Hello, this is the 6th complex numbers video of OCR Pure Core AS Further Maths. And in this session we link complex roots to quadratic equations. In previous sessions we introduced the idea of complex conjugate roots for quadratic equations with no real roots. So quadratic roots are either both real, a repeated real root, or a complex conjugate pair. If we're asked to solve the quadratic equation z squared minus 2z minus 8 equals 0, we might be forgiven for expecting a complex conjugate pair as roots because of the use of a letter z. However, we actually find that it's quite easy to factorise this particular equation to z plus 2, z minus 4 equals 0. Thus indicating that actually there are two real roots at minus 2 and at 4. Indeed, when we draw the graph, we see this is the case. An alternative method for solving the equation might have been to complete the square, which would have given us z minus 1 squared minus 1 minus 8, or z minus 1 squared minus 9. Again, still equal to 0. This form gives us the vertex or turning point as being at 1 and minus 9. You'll note that due to the symmetry of the parabola, it looks as if the vertex, the x-coordinate of it at least, is halfway between the two root values. Therefore, another way of finding the x-coordinate of a vertex might be to consider the mean of the roots. In this case, this does give the same value as 1, but does it mean that it always gives the x-coordinate of the vertex? We will have to explore this for complex conjugate roots. If we consider another quadratic equation, z squared minus 2z plus 5 equals 0, and again because it's not easy to factorise, we'll use the completing the square method, or we could use the quadratic equation. So if we write z minus 1 squared minus 1 plus 5, leading to z minus 1 squared plus 4, we know that equals 0. Rearranging this, we find that z minus 1 squared equals minus 4, thus indicating we're going to be finding complex conjugate roots because we are going to be square rooting a negative number. This leads to z minus 1 equals plus or minus 2i, and z therefore equals 1 plus or minus 2i, giving us our two complex conjugate roots. Of course, we would have got exactly the same result had we solved this by using the quadratic equation. Just as a reminder, the complex conjugate pairs are denoted by z and z star, but it doesn't matter which is which, it's up to you. If we were to sketch the graph of z squared minus 2z plus 5 equals y, then we would find that the parabola does not cross the axis. You have probably been expecting that because you knew that the discriminant was less than 0. So here we have two complex conjugate roots, and what we would like to investigate is whether the turning point or the vertex, whether the x-coordinate of this is still the mean of the two roots. Remember, we can tell from the completed square version of this equation, z minus 1 squared plus 4 equals 0, that the vertex is going to be at the point 1, 4. Therefore, we know that the x-coordinate of that turning point is 1. If we look at the mean then of these two roots, we would have 1 plus 2i plus 1 minus 2i divided by 2. Obviously, with the complex conjugates, we expect the imaginary parts to cancel, leaving us 2 over 2 or 1, which indeed is what we are expecting. Hence it would seem that whether we have real roots, a repeated root, or complex conjugate pair, it is indeed true to say that the mean of the roots will always give the x-coordinate of a vertex. Of course, this does not constitute a proof, but merely an investigation. That was the last video in the Complex Numbers 1 Introduction series.